In the first part of the tutorial, we discussed basic graph algorithms, link prediction by online machine learning, and the notion of temporal walks. This is the second part of the graph streaming tutorial. My colleague Ferenc will continue with online graph embedding algorithms with an experiment on the tennis tournament data. Then Robert will continue with online network centrality algorithms, and finally I will close the presentation with an outlook, conclusions, and again a list of the resources that we used for demonstrating our codes.
In the second part of the tutorial, we will move on to network node embeddings. First, we will discuss the theoretical background, and then I will show you our experimental results with some related Python code. The idea behind node embeddings is to map graph vertices to the dimensions in a way that similar nodes in the graph should be close in the embedded space. This problem was originally solved by matrix factorization, but it was recently revisited by random walk-based methods. A simple solution for node embeddings is graph factorization, where the elements of the adjacency matrix are approximated by the dot product of the node representations. For random walk-based models, the loss function is restricted to node pairs selected from the generated random walks. The field of node embeddings were recently catalyzed by Word2Vec, which is a word embedding algorithm. It is the learning framework for several random walk-based node embedding models. Word2Vec is a neural network with a single hidden layer that provides a low-dimensional representation for each word. This model is trained with node pairs that are selected from a sliding window as it moves along the sentences. Before moving on to node embeddings designed for graph streams, we would like to introduce a few static methods that we used as baseline in our experiments. Let's start with deep walk. It is one of the first random walk-based node embeddings, and it is the extension of Word2Vec for graphs. Here, the corpus is the nodes of the graphs, and the sentences are the generated random walks. The main problem of deep walk was later solved by Node2Vec. Grover and Leszkovec introduced parameters to control the neighborhood exploration process. Node2Vec was one of the first models to incorporate both local and global graph properties in the node representations. The third algorithm that we mention here is line, which is a model that is capable of representation optimization for the first order proximity and the second order proximity as well, which is, in other words, the similarity of node neighborhoods. Our goal was to develop node embedding algorithms that can read data from the edge stream, that are online updatable, that can generate temporal node embeddings, and that are capable of concept drift detection and adaptation. The main concept for these online node embeddings is that the graph data is constantly arriving from the graph stream. For the latest edge UV, we sample some node pairs that are passed on to the online learning process. As we saw before, the streamwalk algorithm is built around the notion of node reachability through time-respective random walks. But there are several other graph properties that can be incorporated into node representations. For example, I have already mentioned an offline method called line that can capture neighborhood similarities. In our work, we also proposed a similar model for graph streams. The main challenge was to define and maintain the time-ever-Jacquard similarity of node neighborhoods. For example, after the latest edge arrival between node U and V, node U and X become similar due to their new common neighbor V. In order to reflect these changes in the embedded space, first, we maintain a multiset of adjacent nodes with respect to their time of arrival. Based on the edge stream, these node neighborhoods are constantly updated. New nodes are added, while old nodes are excluded with high probability. Exponentially decayed weights are used to implement these changes at random. Finally, we maintain multiple hash functions to approximate Jacquard similarity for these neighborhoods by min-hash fingerprinting. Now we will discuss the temporal fingerprint update on a small example. First, observe the temporal neighborhood changes for node U before and after the new edge arrival, which is the UV edge. Here we have the two temporal neighborhoods. The yellow is the old neighborhood before the arrival of edge UV, and the orange is the updated neighborhood after this edge occurred. Node U had three neighbors before, V1, V2, and V3. They occurred in temporal order in the edge stream. As the new edge arrives, the oldest neighbor V1 is excluded from the neighborhood, while the new neighbor V is added to the temporal neighborhood of U. With these neighborhood changes, the fingerprints also need to be updated. Min-hash fingerprints are selected based on the two random hash functions marked by different colors. For example, after the exclusion of V1, which has the minimum hash value based on the purple hash function, this fingerprint was updated for V2 because in the new neighborhood it has the minimum hash value based on the purple hash function. Similarly, V becomes the new min-hash fingerprint according to the red function. So now there might be a new fingerprint match for node X and node U. In this case, this node pair UX is passed on to Virtuvec for embedding optimization. So far, we discussed the theoretical background for node embedding algorithms, and we proposed two methods for graph streams. Next, I will present our experimental results and the related Python code in Jupyter Notebook slides.
Let's move on to online node embeddings. In the theoretical section, you were introduced with stream walk and online second-order similarity. These are two node embedding algorithms that we developed for graph streams. First, we will inspect the related Python code. Then, we will discuss how they can differentiate daily tennis players from other accounts in our dynamic Twitter mention graphs. In the implementation, both of these algorithms consists of two components, an updater and a learner. In the updater, we specify how to sample node pairs for the second component, which is basically an online Virtuvec algorithm. Virtuvec is responsible for the optimization of the node representations. As you can see from the Python code imports, we have different updater for the stream walk algorithm and the second order updater, as they use different strategy for node pair sampling, and they use a common online Virtuvec implementation as a learner component. When we initialize the stream walk updater, we need to specify the half-life parameter, which controls how fast the model forgets old graph information. In this case, we will use 3 hours as half-life for the stream walk updater. Then we maximize the length of the sampled time-respective random walks that end in the latest edge UV. Finally, we set the walk damping factor beta and the number of walks to sample for each edge arrival. The endpoints of each sampled time-respective random walk are passed to the learner component that optimizes the node representations. In the next step, we initialize the online Word2Vec learner for the stream walk algorithm. We use the standard dimension setting for node embedding algorithms. It means that network nodes are mapped to a more than 100-dimensional space. For static node embedding models like DeepWalk or Node2Vec, each node has a fixed representation in this space. But our online models adjust node embeddings every time a new edge arrives in the graph stream. But in order to maintain dynamic representations, we need to use online Word2Vec instead of the classical Word2Vec algorithm that is the underlying learner component for multiple offline node embedding models. The main difference between the classic Word2Vec and the online version is that here we iterate on the sequence of sample node pairs only once. In other words, online Word2Vec uses only one epoch to learn node representations. In our learner implementation, we can set a few extra parameters. Like which Word2Vec weight matrix to export as node representations. Or should we feed the sample node pairs in both order to the learner or not? Now let's move on to the online second-order similarity. In the updater, we need to specify the number and the type of the hash functions that are used to approximate the time-respective Jacquard similarity for node neighborhoods. Before moving on to model execution, I have one final note related to the learner setup. In general, negative sampling is uniform, but here we added a parameter called uniform ratio to control the weight of positive samples when we select negative ones for the current interaction. Online second-order similarity achieved best performance when 20% of the negative samples are chosen from past mentions.
Now we will run streamwalk and online second-order similarity for the first 3 days of the Roland Garros dataset. Node representations are exported in every 6 hours, so we will have 4 observations for each day, starting at 6 AM and then comes 12 AM, 6 PM and 12 PM. With the load edge data function, edges from the edge stream are only loaded for this time interval. Now comes the execution of streamwalk. Here we pass on the streamwalk updater and learner objects to the model container called lazy Node2Vec that handles model execution and the embedding export. Previously, we prepared the streamwalk updater and the streamwalk learner. The model identifier contains every updater and learner parameter. Originally, we used online Node2Vec model container to constantly optimize representations after each time arrival. But we also implemented lazy node2vec with delayed learning to reduce the overall running time. In our case, delayed learning means that node pairs sampled by the updater are stored after each edge arrival, and they are only passed to the learner for embedding optimization at the end of each time window. This way, we significantly reduced the number of function calls in the Python code that resulted in a better running time. For each time window, we print the total running time and the learning time up to that point. For example, for the streamwalk algorithm, execution took more than a minute for the first 3 days of the Roland Garros dataset. And on the right, in the third column, you can see the overall training time of the model, which was the optimization of the embeddings. So what about the second order similarity? The execution is identical to the streamwalk, but here we pass on the prepared second order updater and learner objects to the lazy node2vec model container. We can observe that it took more than twice as much time to run this model for the first 3 days. As you remember, for the streamwalk, it was approximately 1 minute. I want to note that node representations are exported to files for both models to ease further evaluation. The model output directory is returned by the run function for easy reusability. Let's take time for a quick recap. What have we done so far? First, we initialized streamwalk and online second order similarity by setting up an updater and the learner component for each model. Then, we loaded the edge stream for the first 3 days of Roland Garros dataset. Finally, node embeddings were exported after each 6-hour time window as the models were executed online. Now, we will observe how the learn embeddings behave over time. For the quality check, we will use the temporal node relevance labels available for us in the dataset. As you remember, based on the official event schedule, we could assign a relevance label for every Twitter account in the dataset that changes from day to day. The question is to see whether our models can differentiate between daily tennis players and other accounts on a given day. But first, let's load the relevance labels and the node representations. For this task, let's import 2 functions, the getDataInfo function, which loads the labels for the days and the Twitter accounts, and then we load the representations that were exported in the previous step with the load node2vec features function. As you can see, we load 12 representation for every node in the data, as we had the 6-hour time windows. I prepared an animation with the Python plotly package to observe how the embedding of tennis player accounts change over time. Unfortunately, I couldn't make the animation work from the slides, so let's change the view now. In this animation, we will observe how the embeddings of tennis player Twitter accounts change over the first 3 days of the Roland Garros dataset. Originally, nodes were embedded in a more than 100-dimensional space, but for the visualization, we only use the first 2 coordinates. Daily players are marked by red, while blue nodes are players who do not play on the given day. For the red nodes, we can observe tennis game-related metadata as well. For example, in this case, we can see that the game is related to a men's singles tournament, and it has taken place in the Philippe Chartier court. Node representations are initialized uniformly at random, so after the first time window, every node is close to the origo. As the simulation unfolds, you can see that by the end of each day, red nodes are well separated from the blue nodes. It means that our online embedding models can differentiate daily tennis player accounts well. At snapshot 3, it is the end of the first day. We can see the cluster of daily players on the left. At the end of day 2, we can also see a good separation for daily players from the inactive players for the day, and it is also true for the third day. I would like to highlight that during embedding optimization, the models did not receive any label information, so they managed to identify daily tennis players only from the network dynamics. Let's observe the representations for online second-order similarity as well. This model uses a longer half-life for time decay than StreamWalk, so the embeddings are more evenly placed in the space. The representations have a real story to tell, so let's discuss the dynamics a bit further. At the end of the first day, red nodes are separated well from blue nodes. As we move to the next day, we can see the cluster from the previous daily players. Now they get the color blue as they do not play on the second game. These nodes from the previous day are slowly moving back towards the origo as they are not considered anymore a hot topic on Twitter. By 12 p.m., the cluster of new daily players emerge in the opposite direction. Again, by the end of the second day, the separation is much stronger than during the day before. But one question remains. Why do these players remain so close to each other when they only played on the first game? Now let's see their names. Adrian Manarino, Tommy Robredo, Alberto Ramos Vignolas, és Horacio Zeballos. Now, if we move to the the third day, we can see these nodes again. They are red, so they play on the third day, and both of them play in men's double tournaments. So, our model was able to catch chatter related to next day events. In order to compare the performance of our models with baselines, we implemented a similarity search task. We used normalized discounted cumulative gain, or NDCG, to score the similarity top list for daily player accounts. NDCG assigns higher score if daily player accounts appear with higher rank in the similarity list. In our experiments, we computed the average NDCG for the top 100 closest nodes for each daily player over every snapshot. Dot product was used to determine the similarity between node representations. The related Python code can calculate NDCG for different players and snapshots in parallel that can really speed up the model evaluation process. Based on our measurements, we can say that StreamWalk and second-order similarity achieve very similar performance. But as we saw in the previous animations, the representations behave in a completely different way, so they have the potential to learn different network properties. That is why we experimented with a combination of the two models. First, we tried feature vector concatenation, a method that proved to be successful from Tang et al. In case of the line static node embedding. Unfortunately, it did not work for our online models. Finally, we combine the output of stream walk and second-order similarity by using the weighted average of the corresponding inner products as similarity. Surprisingly, for the first 3 days, the second-order model has higher weight in the optimal combination. But I would like to highlight that in this demo, we only inspected the first 3 days of the dataset with a single instance for each model. In the paper, our results, based on 10 independent experiments, proved to be more consistent. Here, the second-order model achieved lower combination weight for both the Roland Garros and the US Open tennis datasets.
In this part of the tutorial, we will discuss network centrality metrics and the way of defining them on edge streams and temporal network data, and also the potential pitfalls and problems arising when defining these from edge streams. The concept of these centrality metrics will be based on time-respective paths. These are relevant concept on edge streams, and basically they only mean that they connect adjacent edges that are ordered in time. These may model a flow, for example, an information flow in social networks or flow of funds or goods in the economy. The concept is that if a delay between two adjacent edges within a network is small, then a flow is more likely across those within a time-respective paths. One way of defining then centrality based on these time-respective paths is just to simply summon those ending at a certain node at a certain time. That is basically the definition of temporal cut centrality. Temporal cut centrality is defined on edge streams, and it is nothing but the weighted sum of all time-respecting walks that end in a certain node. Here we provide a toy example to show all the temporal links ending in a certain node at a given time. In the left we list 5 different edges. First, A and B forms a link and T1, and then finally there's a link between E and U nodes at T5, and all these 5 links are ordered in time. T1 is the earliest, T5 is the latest. Once these temporal links are observed within an edge stream, then at a certain time T, which is greater than T5, in a single node U, here we list on the right all the time-respecting walks that end in node U. So these are then the walks that end in node U, and once we discuss like how do we weight those, basically the weighted sum of these links will be the temporal cut centrality of node U at time T. There are several ways of defining then weights corresponding for these time-respective paths when aggregating those and compute temporal cut centrality. One way of defining weights over time-respective paths is to define weights for each pair of adjacent edges. For example, in the below example, there are edges appearing at T1, T2, and T3, and then weights are defined between T2 and T1, and then there's another way defined based on T3 and T2, etc. And then we simply just multiply these weights, which basically capture the time difference between the adjacent edges appearing in the graphs, and then this multiplication will result in a final weight corresponding to a temporal time-respecting path within the network. The final definition then of temporal cut centrality depends on the weighting functions that we use to score adjacent edges along those time-respecting paths. One potential way of defining it is just to set up a constant less than 1, and then a walk length is then penalized, so like longer temporal walks will be less likely within temporal cut centrality and will have smaller weights, while shorter walks consisting of less edges will be more likely and will have higher scores within the weighted sum of temporal cut centrality. Another way is to explicitly include time in the definition, and with a certain exponential decay score the time difference between the adjacent edges appearing in a time respecting walk, and then this will result in a definition which not only penalizes the length of the walk but also the length in time with an exponential function. Based on these two, we may ask, is there any connection between temporal cut centrality and cut centrality defined on static graphs? And well, the answer is yes. Given an underlying graph with an edge set of size E, we may sample uniform random T edges simulating a uniform stream from this graph, and over this graph we can calculate the expected value of temporal cut centrality and compare that to the actual definition of static cut centrality. Depending on the different weighting schemes we use, we will end up with different results, obviously. This first slide shows the final derivation of temporal cut centrality, which is certainly related to static cut centrality when we apply a static beta weighting scheme to calculate the weights of adjacent edges in time respecting walks. And I kindly point to you our paper where we basically derive a similar form in case of an exponential decay, where we basically prove that temporal cuts converges to static cuts on uniformly sampled edge streams. Next, we show that temporal cut centrality can be computed in an incremental way from edge streams. Basically, we'll show the concept that computing cut centrality from edge streams is simple and it can be done in an incremental way. When a certain edge, say VU, appears at time t, VU, then we may realize, as shown in the figure at the bottom, that the centrality of node U, since it is based on time respecting walks, will increase since a new walk, meaning the new edge V and U, will appear and will end in U. And also, besides that, all the walks that ended in V will continue via edge VU to U. So at the end of the day, the total increase will be as shown in the formula in the side, and this will pave the way of a recursive definition and an incremental computation of temporal cut centrality from edge streams. To showcase the applicability of cut centrality in real data sets, we will use temporal cut centrality on the Twitter data sets we introduced before, specifically on the Roland Garros 17 data, where the nodes are Twitter accounts and the edges between them are user mentions, and the ground truth labels that we will use here to somehow evaluate the different potential temporal centrality metrics from edge streams are the fact that we know which players are participating in a given day, and we will try to capture that with various temporal centrality metrics. This slide shows the predictive performance over time of the different algorithms, and we can conclude that temporal cuts is basically the best across several static and temporal results, and show the actual applicability of this simply defined temporal centrality metrics from edge streams. We must note though that temporal cuts is not the only temporal centrality metric. One closely related result is temporal PageRank from the paper of Polinar Rosenstein et al. We kindly point you to that paper as well.
In the past 1.5 hours, my colleagues have surveyed results to analyze and model edge streams, with examples including interactions in a social network service or even queries in a graph database which needs real-time updates from an edge stream. The ingredients of the algorithms included the data stream computational model, the notion of temporal networks, temporal walks, edges that come in the stream, and very importantly, the frequential evaluation method that allows a model to be evaluated immediately after a new edge arrives in the stream and the model is updated, changed, and immediately evaluated for each single edge in the stream. Algorithms that update the results while the edge stream is processed include traditional graph properties, sampling, subgraph counting, graph query evaluation in graph databases, low-rank application, with the most important application is link prediction, network embedding, which we use for similarity search, and finally network centrality algorithms. As an outlook in this presentation, let me close by discussing briefly data stream processing systems and the notion of concept drift detection. Distributed data stream processing algorithms arise when we have to process a data stream that doesn't fit into the resources of a single machine. The easiest and typical way to train models is using a single server, maybe multi-core, maybe a GPU, but still in memory and using static data. Distributed is much less convenient. We need to install, manage a cluster, optimize the performance, and as a factor in using distributed data processing less frequently is training labels are rarely available in huge quantities, so we rarely need to train very large models. Online learning seems like a small niche application at the moment. Distributed and streaming applications include Samoa, a standalone library with connectors to many stream processing engines, Spark ML, although Spark can process streams in mini batches, Spark ML methods are typically batch. Flink machine learning libraries are under development with relative low community support. And actually what we see in this area is training huge models is probably less important, but serving from large streams, infinite streams of data in a distributed manner is a very important application. In the chart on the left, on the right, we can compare different systems regarding whether they train models batch or online, and whether they are non-distributed or distributed. Traditional software like scikit-learns fall in the batch non-distributed area. Non-distributed online streaming is the MOA library, which was extended to distributed systems by adding connectors to the Samoa library. Certain older systems, for example Mahout, process in a distributed manner but with static data, and the niche applications Spark and especially Flink work in the area of distributed and moving towards streaming applications. The last concept I'd like to introduce is concept drift. If we recall the success of online methods against their static counterparts in two applications. One was recommender systems. Users can have different moods in different user sessions, and we need to quickly relearn, for example, the user current mood and taste. And also link prediction, that was the application we showcases the most, are used for similarity search, centrality in social networks. These can be affected by events in the physical world, for example a tournament schedule, and traditional learners assume finite, static, identically distributed datasets compared to the data stream processing, where we can very quickly adapt to changes. To detect the concept drift, a very early result that introduced the concept detecting decision tree learner was by Halton, Spencer, and Domokos in 2001. They evaluated their models with web page request data. For a survey and performance comparison, still mostly considering tree learning, Gama, Sebastiano, and Rodriguez evaluated several streaming algorithms, and they introduced the notion of the frequential error estimate to detect the concept drift that's connected to the frequential evaluation model, but here detecting the drift by showing the changes in the frequential evaluation performance of the classifier. And finally, Sliobaite and co-authors introduced 6 challenges that are still up and active for adaptive learning systems. These 6 are making learning systems scalable, evaluating them with real data. This was the reason why we introduced the tennis data collection. We need evaluation data that has the temporal effects and temporal labels, usability and trust, integrating expert knowledge, considering the application needs, and from algorithms turning to actual toolkits. For the resources in this tutorial, first of all, I'd like to draw attention to the GitHub page of the tutorial that includes the Twitter graph stream generator, the online graph embedding algorithms, and the link prediction by online machine learning, which is based on our older AlpenGo toolkit. And the papers we mentioned in this presentation in temporal order, starting from the oldest to the newest results, include our first recommender paper that considered temporal changes, the papers related to the recommender systems 2017 tutorial with evaluation of the online ranking methods and introducing the AlpenGo software, our temporal walk-based centrality result, then the node embedding result, both of these results using the tennis tournament data for evaluation, and a very recent result using node embeddings for de-anonymizing Ethereum users. As a conclusion, graph streaming has several applications for monitoring online events. The advantage is that streaming algorithms can react faster than the static counterparts and perform much better than graph snapshot-based methods, but they have a computational challenge to update the models. Several algorithms have appeared in the data stream computational model starting around year 2000. Our methods, most of them are actually semi-streaming. They store relatively large representations in memory. However, fast update is crucial in our results. In the name of my doctoral students and my former student Robert, I would like to thank you for your attention.